measurements of 3 days, then I get 0.2, and then again after, I don't know, 2 years, I made a third one, and I put the straight line, and that is my volume in place. What I'm producing from that volume in place, that is my recovery. That is all what you need to know from this when we use. So basically, this is P over Z plot when we use constant pressure, constant rate in a boundary condition. That means so-called well test analysis. When I put constant pressure, I'm in rate time analysis. In rate time analysis, we are using flowing material balance. So that is practically all what is a repetition from yesterday. And also I want to be again very clear that yesterday what we did, we only presented the, I'm not able to remove these guys. Why that? Okay. Raise. Yes, we were able to only use well coupled to the reservoir without fracture. Now we are introducing fracture. This fracture can be along the vertical well. Usually these are then so-called longitudinal fracture. So now we will first define what is longitudinal and what is transversal. When I have a well, okay. When I have a well, my fracture can be like that, or is a vertical well. This fracture, that means along the well, I have a fracture. So connectivity is in this region, in this area, over that line. That line is connectivity. Well line, this is one here. This line is my connectivity to the fracture, okay? So I am now, so this shape of the fracture is longitudinal. But when I have another type of the fracture, which is going to be, let's say, like that fracture, then I have this point here, and that is connectivity is very only through the connection of the tube. You know, this is your, of course, tube to the fracture. Then it is transversal fracture. So today we will talk a lot about longitudinal and transversal fracture. Now, of course, most of the time in vertical well, what we are doing, we can make both fractures, and we will see later on what is the consequence of that. Okay. Then next is, okay, well, let me have another well that is going to be horizontal well. Then my horizontal fracture is like a longitudinal fracture is like that. It's like here I'm using that well, part of the well is connectivity to the fracture. Or I can have again a point, and at that point when well is penetrating the fracture, that is the point which is my connectivity. So all the flow goes like this to that point. So it is a very narrow corridor when you are coming in. All idea, you want to make a huge drainage, and that is this cloud around here is your drainage, because you want to drain more and more reservoir. So as you see here, this drainage is also quite high thanks to this plane, because what is fracture? Fracture is really well, plain well. You can say like that. And what is your well? Well is, let's say, tube only which produce something. And here I have a plane that produce something. Why? Because connectivity is coming on both sides, from this side and on that side. When I have only the well, You see, Welles connectivity is only in that point, you know, when I have a perforation and all the well, you see? But here I'm extending by fracturing. That is the whole, and of course it is the biggest business these days because it's easier to re-perforate your fracture or make a new fracture than to drill the new well, of course. So now today's lectures are really on multi-fractured horizontal well. I name it as ML. MF, it's really a mistake. And then I will talk about, so that is multi-fractured horizontal well. Then I talk about analytical model. First, we gave an introduction, then we go through the analytical modeling, and then these are cases from UK, then cases from Norway, and then the reservoir simulation. First two cases are semi-analytical or analytical. That means I have an analytical screening simulator. It's fully three-dimensional, heterogeneous, but it's monophase. Analytical models are mostly always monophase. And as well testing is also analytical model, immediately you can say that, okay, this model is derived by the diffusion equation. We yesterday talked about diffusion equation. Otherwise, reservoir simulation model is more capable, maybe in catching very many physical property from the reservoir and modeling it, because it is solving non-linearity by introducing a method of numerical method finite differences, not finite element. Finite elements method can be used when we discuss how we create fracture. It's a small model, different models. And these models use finite element method because in this you have to be very precise how you make. And that is mostly part of the mechanical engineering, by the way. So basically, this is for today. And then in the second part, we will talk about multilateral modeling and simulation, and then we will show you certain multilateral cases. I will first go through the case I did personally. So these two models here, these two models here are really my work. And this model here is also my work here. The rest, okay, I will say that it is somehow combination with what I experienced by exchanging the knowledge or cooperating with someone. So basically this is in short. And I would like to say that today we do consider multilateral technology well developed, that it is really in use, and particularly multi-fractured horizontal wells. Because when we are approaching tight reservoir, more complex reservoir, the only resource today to solve the problem more efficiently may be due to thanks to the technology of multi-fractured and multilateral wells. Okay, so you see, in general, when we talk about horizontal well compared to the vertical well, we can increase productivity index, which we know it's the Q divided by delta P. We also know that that is the Q. The delta P is really your P reservoir minus bottom hole pressure P, BHP. That is at the bottom of the well. So if I have the well here, this is my bottom, that is my BHP, here is my BHP, and then I have pressure reservoir somewhere here. This reservoir pressure difference brings that rate up. This rate is bring up thanks to the delta P difference in pressure. So with this, I'm able to create productivity index, and this index for horizontal increases up to 6 times, that is really significant. So that means it is almost like I have to drill 6 wells. So it's not, it is very efficient, by the way. If the system works, sometimes the cases could not work. So we are talking about successes in the ratios, technical successes for successful well, 95%, economically you're over 50%. You accelerate production, you increase the reserves. So that is the whole idea. So what are reserves? Reserves, if this is my volume in place, and these are the reserves which I can take out, okay? So with this, we are able to accelerate how we, in a shorter time, we produce more oil or gas or condensate, but also we increase, you know, the reserves, let's say from certain quantity, which was marked, which can be marked like this, to this volume here. So this difference delta volume, delta V, is thanks to the horizontal drilling now. So, but in a case then it is a failure. In most of the in United States, the failure to in a certain date was about 30%. And that horizontal wells show no reserve increase. And and from that quantity, 30%, almost 93% were not successfully economically. So you may have a problem, you may drill the well, and you may lose the money. So the petroleum engineering is extremely risky business. That is why you have almost very often that very many companies are just collapsing because the process is, or you may be unlucky. Then you know the company where I used to work, after the first my retirement, what happened was that they drilled I don't know 3 negative horizontal wells, which I'm now talking about in Denmark. And what happened really, they have to solve the company. Now the company is named Spirit Energy, and it's quite a good company, but they lost a lot of money. They lost several $1 billion. And of course, in this case, you have to move out. So hydraulic fracturing is a stimulation method that what we are trying to improve the production by introducing fractures. The fracture creates a high conductivity pathway into the formation. That's all. So horizontal and multi-fractured wells. Of course, we are talking about vertical deviated or horizontal deviated wells. Usually very complex connection between fracture and the well bore appears. And then solution is to plan well correctly, azimuth of deviation section parallel to the maximum horizontal stress. So that is the very important, because the way how we are making fracture, we will discuss that later, are related to the stress analysis. So rock mechanics is important part, which can be also, because you have also the material stresses. So you as a mechanical engineer are well educated, even better than many others, to learn that technology, okay? Drill S-shaped wells to penetrate reservoir with vertical well bore. These are so you see 3 different shapes, uncontrolled well bore azimuth, then a well bore azimuth parallel to fracture azimuth, you see. In this case, I'm talking about the fracture that is transversal fracture, which we discuss. What is now? Okay. Yes. Okay. I lost something on my with my pen. So as you see here, I am in this area here when I'm trying to You see, this is the only point when I have in one point, that's the really point, I am connected my well to the plane, and this plane is my fracture. Here, my plane is along the well. So this one is longitudinal fracture, and this is transversal fracture. And then this one is S-shape. That is very interesting how that works also, because also this should be transversal fracture. See, but the well is S-shaped. Here's my vertical well, which is, let's say, you're talking about horizontal well, and this is my S-shaped well with transversal fracture. So these are the things which somehow usually it's not very ideal always. So you have to deal with a different. You have to know the trajectory of the wells, and you have to know the shape of the fracture, and is it transversal and longitudinal? Just sorry. And case, you can have open hole fractures or fractures when you don't have a casing, but easier connection between fracture and well bore, it can appear. You are saving, because if you put any casing, that means the pipe, almost the pipe which is connectivity to the rock, because you want to keep the well that it is not going to have any incidents, in a sense that you will have a problem that because of rock falling into the well and so on. And then you have also possibility to create so-called liners, and then you are using cementing, and then all these processes increase the rig time. That means the process how you are not producing, by the way, and your management mostly like to reduce this rig time as much as they can. And then specialized system required to isolate individual section to control fracture initiation. So it is quite a complex and very expensive work. And I will say that what is most important, that you have to know that you are always with the fracture perpendicular to the minimum horizontal stress. So this is your the transversal fracture. No, this is your longitudinal structure. And you see with this, you are perpendicular to this, to the fracture, longitudinal fracture. And here, opposite, this is perpendicular to the transversal fracture. And here you see that also this is perpendicular to that. So this, you can say that this is the 90 degrees, and here you have here 90 degrees, okay? That is perpendicular, okay? So with this, you are somehow, this is basic for what you are getting, and then longitudinal fracs are easier to pump and have the simplest connection to the wellbore, of course, because you don't have a huge pressure drop in the point when there's a connectivity. Then post-fracture production is not choked at the contact. Usually we say that in previous one, we have a problem that here you have a choked. Everything is flowing in this point towards the pipe, and you are choked. And what is the most important, that wellbore must be drilled within plus minus 15% of the maximum horizontal stress azimuth. So now we will, in the next showing, I will show you what is the consequence. Usually you make longitudinal fracs as you have several transversal fractures, you see? So that means you can somehow see that that this is the benefit of the biggest longitudinal one. So basically, so in this case, I have here longitudinal fracture, and here I will have, let's say, several, you can say also transversal, but now I'm putting that length to that length, and that is how we usually define your potential of the longitudinal fracture. So, but definitely you have to know that why you are doing fracturing is instead of having, let's say in this case, 5 instead of having 5 wells with one longitudinal fracture each, you decide I'm making one long horizontal well, and along them I create 5 transversal fracture. And then I can say, yes, but instead of that, let me do that. I put one vertical well, and then I put, instead of having these 5, I just put, let's say, the length of the 5 fractures, which is B, which is somehow emulated. So I have now longitudinal, but with a half length of B half. We will talk about that soon, so you will know what is half length. So basically, when we talk about the fracture, we are talking always about this part here, which is what is your length, and then we introduce XL, that is half length. Then in addition to that, that fracture, if it is going to be, has a certain conductivity, it has to have a width here, so that this name is omega. So omega and half length, these are the only thing which we have. And then we have to know also, when I have omega, definitely I have a fracture conductivity. I will put F small is a fracture conductivity, but I have also here the rock conductivity, K, of the formation, F. These are the basic parameters we have to remember, because soon when we will discuss, okay, I'm not able to do this. When we will discuss soon how we further proceed with calculating and modeling, that these are the basic parameters we have to find, because we have to define the dimensionless fracture conductivity. So for that, we should understand how that is defined. Usually, as you notice, we are using a lot of dimensionless number. That is the only, first you have to use dimensionless number of rate, pressure, and time when you're solving partial differential equation. In addition to that, when we are making any normalization of the system of equation, we are using dimensionless numbers, okay? Designing longitudinal fractures, then start to equivalent single fracture or vertical. So that is what I presented earlier. You start with the equivalent single fracture of vertical well bore, use a unified frac design to design geometry of a single fracture, and place multiple fracture along the horizontal well. So complete number of fracture. So these are the procedure of the workflow, let's say. Then unified frac design, proper number. Okay, this is when you are creating fracture, that you have to inject something what is keeping the fracture not stanked. That is you are injecting propan, and propan means that I have now parameter omega. So that means the following: this is my fracture, and this is my well penetrating the fracture. So now I have here omega parameter, and this omega has dimension of L, which is the distance, okay? So this is very important because, of course, this is the case when I have a longitudinal fracture. If I will have another fracture that is going to be the transversal fracture, then I will have I will have this, and then I will have that point, which is going to be point to this plane. So that also can be also, you know, the frac which is going to be made transversal frac with the propan, but this propan then will also have omega here. See, this is going to be your distance, how there is a certain permeability which is huge, and with this permeability you are flowing to the well. So basically, you always have to, whenever we talk about fracture to matrix system, we have to have two different things to understand. What is storage and what is your transmissibility? Fracture means I don't have a storage of the fluid inside. These are like corridor in any house you live in. Corridor are a measure of how your system is able to make transportation of the fluid or the people. Rooms or places where the people can be put to live is the storage or fluid. So you have always different things in between storage and the fracture system. We will discuss that if we will have today time, when I will talk a little bit about fractured reservoir in detail. So just a moment, just to clean this. So now this is the most important part. You see, CFD, that is the ability, that is this number which is very important, the ability of the fracture to deliver reservoir fluid to the wellbore. Okay? And then that has to be divided with the ability of the formation to deliver reservoir fluid to fracture. To see, this is the very important. So one thing is here that I am delivering reservoir fluid of the fracture to the wellbore. So this up is really your connectivity. You have here connectivity fracture wellbore. Okay, and here is down divided by the ability of the formation. So that is okay, let me be consistent. So I put fracture small f and very big F is a formation, or formation to the fracture, to the small f. See, further to the FR. So basically, you see, this is your some kind of the you have fracture to the wellbore, and then you have formation to the fracture. So the dimensionless fracture CFD is a measure of how effective the propan fracture geometry is at the draining of the formation. So basically, this is some kind of important parameter, because without that parameters, you are not going to solve the system of equation. And then you have always, for the longitudinal fracture, we use NP to calculate the optimum dimensionless fracture conductivity. And CFD gives the best possible combination of propan length and the proper width, and optimum fracture length, XF. So that means what is length again. If I have a wellbore, then I have a certain fracture. This fracture has a height and it has a length, this length, so that from this point to here. usually we introduce XL, which is just half of that, is the 1/2 of the L, of big L, okay? So that means, and then in addition to that, if I have a certain type of the fracture permeability, which is uniform flux, infinite conductivity, and finite conductivity, then with the finite conductivity, I introduce here omega. These fracture types are related to the, if we have any let's say, restriction to the flow. If there is no restriction to the flow, we are talking about uniform flux with or infinite conductivity. And when we have restriction to the flow, then we are introducing the omega, which is finite conductivity. So this is very important because we always have to put what is my K permeability, because this K permeability is going to be different for three different type of the fracture. This H1/2 XL, this is just how much you are exposed to the reservoir. So that is again how much the reservoir will feed fracture, and then we have always to consider that that is going to be the one parameter. Another parameter is how fracture is going to feed the well. That is all. So you're feeding first from reservoir fracture, then from fracture you're feeding well. And then you have these two numbers to combine, and that is coming into this CFD. Okay? Doesn't. And then in addition to that, we have to introduce dimensionless now productivity index. So with these parameters, this is all what probably is more important to, but that is creation of the, I'm not going to talk too much about how the fracture are created. I'm just putting the main terminology we have to know for that. Because this is another probably topics, and that is another course, at least 3 to 5 days course, is to how creating fracture. We are not talking in this course about how we are creating fracture. So the angle is the most important part of fracture from wellbore. So most wellbores are drilled without knowledge of the azimuth. That is the azimuth, you see. And then without that knowledge, you will produce the transverse fracture. Okay? So transverse fracture have a poor connection to the wellbore. This makes frac jobs hard to pump due to tortuosity. This shocks production and dramatically reduce fracture effectiveness, and open hole fracture have a much cleaner connection between the fracture and the wellbore than the cased and perforated fracture. So this is again the structure of the well. Do we have the open well, or we have a cased well? So transversal fracture, that is the ideal. And what is here very interesting, you see here that we have different, you see this? These are going to be your drains. Under ideal conditions, and what do you think? How many curves you will have from this system here? Hello? Presuming that my drainage here, 1 is equal to the drainage 4, drainage area, I think. And then I will have drainage 2, and here I will have a drainage area 3. So you see here, in this case, what you will have the following, that this is your drainage D1 and D2, and in D and D4 will be same. And drainage, D, that is going to be only one curve, which is going to be related to D2 and D3. So these are, they will just overlap. If I plot cumulative rate versus time. It can be also for the rate. For the rate, it will be just the same. I will have in the rate, then I have a different plot. This plot is going to be like this. I will have down. I will have here D2 and D3. And then I will have here D1 and D4. Why? Because this is much bigger here than this, because this is squeezed. See? So that is interesting. That is ideal condition. You will see, it depends. This is, and you will see I'm using such a simulator, which is transient simulator, which I did for BP, Conoco, and Philips when I was doing the work with Institute for Energy Technology, Norwegian Institute based in Trondheim. And you will see later all my studies based on that, okay? Of course, if you have more physics into it, it will be different. But this is just ideal to understand how how we are modeling. Now we have transverse fracture. You have productivity per fracture. As you see, the shape is different. My shape is different because I'm telling you that this is going to be maybe like that. But here, of course, he has a difference. Why? Because when you have a well which goes like that, this is your horizontal well, and these are the fractures. You will have here the huge pressure drop, you see? Or no, sorry, it will be here, vice versa. It will be huge pressure drop here. So just for that, get that. This is your well, and you are producing here. And then, of course, here you have a huge pressure drop, you see, compared to here. See? So this is also, you know, with reservoir simulation, you can establish such a profile. So the open question is how many fractures we need. It depends on the half-length permeability of the, first of all, what you have here. Now we will just plot here. Here it depends on what? This is my XF, this is half-length of the fracture, and if this is my well bore, then it is, then I have here fracture K permeability, okay? I have K from formation, FO. And then what else I have? Okay, I have the height. I have the height. And I may have also the omega here, but it depends if my flow is finite conductive, C, FC. So these are the basic. Then here what we have that here we touch everything. XA, XE, it will be also the size of the area you are producing. So all this has to be considered when we are making a model, and I will show you later the basic mathematics of the model we created when made a semi-analytical modeling approach. Just a moment. So here is the transverse fracture. This is the gas well. Near wellbore, we are getting choking effects. This is the most important thing because you have here the huge pressure drop. This pressure drop is causing that you may have some difficulties and you are not going to produce as expected, as you will have with the longitudinal fracture. And also it can have serious effects in medium and high permeability gas wells. So this is also to be, and that was done by Economides and Martin. And all these slides are, by the way, the copied from their work. Transverse fracture, gas well can be also in addition turbulent, and that combined with the choking effect can reduce fracture productivity for 90%. This is very important. And now we can see here that type of the completion is which type for the gas well. Usually, you know, when I started working on fractured reservoir and this naturally fractured the artificial fractures, then we came to Phillips Petroleum Company with the proposal that we should develop the model for horizontal well. Then the guy who was Norwegian trained in the United States, that was Phillips Petroleum Company. So I was after the budget to get to the institute some kind of the money, because we used to have in Norway a budgetary system, not budget. So with this, what he said, okay, and we are not interested in horizontal well. Not horizontal well, we want multi-fractured, MHV, multi-fractured horizontal. And then they said, okay, if you can, give us proposal that we want to go along the horizontal well, 100 fractures. So we went, and then fortunately, I was always very lucky to work with the good mathematicians. As I studied my first degree in physics, we went to the Saint-Étienne conference in France, and we discussed, and we came to the proposal, and we managed to get for development of the software $1 million for BP, Conoco, and Phillips. That was probably the best part of my life, because we really enjoyed it. And you will see later, it was one of the probably leading software in the time when it was done. And I will show you that the software today. So here, permeability. For permeability, so now I'm talking about formation permeability. For bigger than 5%, horizontal wellbore longitudinal fracs will come in all cases. You see, it strongly depends, the fracture depends on the formation permeability. From 0.5 to 5, we can expect a longitudinal or vertical fracture. And again, depend upon relative cost of vertical and horizontal well. So it depends what is cheaper for you in whatever circumstances you are put. From 0.1 to 0.5, horizontal wellbore transversal fracture. So above 0.5 millidarcy, the choked connection means that the transfer fracture are relatively inefficient. You see, this is very important. And when it is less than 0.1, horizontal wellbore transfer or vertical fracture well with the fracture depend upon relative cost and vertical and horizontal. So you see, this is pretty, now we have, based on the experience, disconnected setup, which can be interesting to be today put in the expert system. Because, oh, what is going on now? Sorry. Because why? Because because you can teach today machine to replicate your knowledge, and with that, I don't like it. I'm not so sure how I can remove this now. Oh no, it is okay. So you see, so that is all what I wanted just to make as a comment. So now the open question is what we are going to do and how we are going to solve the problem when we have a horizontal well. Should we put transversal or longitudinal fracture? We have to look at the table to get some kind of the expert who is going to help us. That is, we are creating fracturing. Now, after that, we are going to talk only how we are modeling fractures. Then we have to consider formation stresses, well bore azimuth, gas, how many fracts. No one knows, this is a building. It is when you're building a house, 5 floors, you build a house. But here, the architectural design defined that urbanistic plan. But here, we don't have any urbanistic plan. We don't have any knowledge. It just happened. So that is why I was discussing most of the time when we come to offer a service company, but they say, no, we are just doing as we learn. So that is okay. Then we have fluid recovery, rig time, how much you are taking rig time, because this is very expensive. You are occupied, you are not producing. So that means you have to be very efficient and very fluent in what you're doing. And then operational flexibility. And you always have to ask yourself if the vertical well will be better. So here, once again, we have to know that the objective of the fractured horizontal well is to create a system whose long-term performance will be identical to the single fracture length equal to the spacing between outcome fractures. You see, this is what comes from Raghavan. This guy was an amazing guy. Raghavan, and I work with him, by the way, because he was paying us. He was in the same time developing software, which we did, but we have a better solution and more robust software than he did. So they got our source code. I don't know how they use it, but afterwards. But in that time, I have to go to Bartersville, to United States from Oslo, to convince him that our model is well done, to be paid further for each year. I have to fight for the budget. So what is here? What is here telling me is I have the objective fracture the horizontal well is to create the long-term performance. I will have that these 4 fractures will be equal as a single fracture of that half length, you see, and of that width. So this is going to be the width, you see, and that. So that is how you create it. So now you have to ask yourself, okay, but how I'm going to in hell calculate that? You will see later in a minute what I can do and how I can create that. So now let me, okay. I thought that okay. So now I have, once again, that is in the last overhead discussing this. I have this CF effective number, which is going to be K effective multiply fracture length. And here I have also this CF, which is now going to be KF multiply omega F. So this is interesting as a transversal fracture versus longitudinal. So that is the goal of the overall system, how you create very many perpendicular fracture on this, which we name as a transversal fracture, compared to one longitudinal. Then we have to use horizontal well fracture configuration. We have transversal fracture and longitudinal fracture. Then we have microseismic mapping. And this mapping are helping us that we are defining the space where we can do the fracturing. Now it's up to the system how they will create the fracture. That means to the expert to create the fracture. And here is, more about what we discussed earlier, okay? And here, the more thing which is coming is naturally fractured reservoir. Naturally fractured reservoir means that you see what you have in a naturally fractured reservoir. This is the model. In this model, what you have, in addition to the fracture which is done artificially, you see, you may have the fractures which are like that, you see. All this here, you see. So ideally, the question is now, if I ask you, where are you going to put your fracture? Ideally, you should put your fracture, if this is your horizontal well, and you have here, let's say that you have here like this fracture and then that fracture, you should position your fracture here, you see, just to be sure that you are using corridors which is going to help you, because you are using the natural fracture then, you see, you put your fracture here and then you will flow all around, see. So you are almost having like artificial multilateral well around, which are the corridors of the fracture. That is what is fracture system, is multilateral well. So this is in connection to the second part of the introduction, to the second part of the talk, which is going to be to multilateral, by the way. So then my lovely question to at least when I teach this course is, what is my horizontal well at all? So what is my horizontal well? Let's say that this is my fracture, you see? This is my fracture. And then I put fracture which is like that. And then finally I put the fracture which is like that. So you see here I have a half length XL, which is big number. Then I have a smaller XL. And here I have that my radius of the well is equal XL. You can say, yes, this is my horizontal well, is my longitudinal fracture, which height is equal, which half length is 1/2, if which half length is 1/2 of R. Yes, R. Yes, because R is going to be 2XL. Because here you will have this, and then you will have, this is your R. But basically it is really, this is your radius. This is your radius. And and that is going to be your XF. Yes. So it's, no, I was right. So that means R is equal XL. Yes, sorry. Is equal XL. Okay, so that is what is your so if you don't have any solution for horizontal well, you can you can put long horizontal well, and then you just make a simplification, and you will get some responses on that. Okay, so this is now the something just to probably not. So the lecture 2 is really more interesting. Let's say, just let me see now the timing. 2:36. Okay. See, I will first go very fast through the mathematics. Multiple fracture horizontal well. For that, we need to have a series of solutions corresponding to various conditions and of the model. we have first how to set up the model. The model, we can say it is slab model. What is mean the slab model? Slab means if I have here the horizontal well, and then I make the cut of the space. Slab is that cut here. Slab. Usually this is mathematical. And slab means I have here infinite boundary. And if I have here that the model is given like this, and then it is going to be like that, then I have a model which is in the box. In the box, I have no flow boundary. We know from before yesterday lectures that when I am in this model here, now we are coming back to what I spent yesterday, almost a day, just making a good introduction that we easily follow each what we are doing now. I'm here, when I'm here, then I want just to I have these curves, you remember, which are concave upwards, and then I have curves which are concave downwards. These downwards belong to that part here. This is depletion or a bounded reservoir. This one is so-called transient, and because of these open boundaries, I'm here in transient mode. So I'm going to use here for this analysis, and here I'm going to use in the next one is the box model. I'm going to use this one, solutions. And that is both defined only and only but by our outer boundary condition. And that is in this case, of no flow, and here no border, that is transient. How long this lasts? You will be surprised. This can last in time, transient response, maybe 2 years to 3 years, or even more. If you have a horizontal long well of 7 kilometers and you have about, I don't know, 34 stages on it, or fractures. So, and then the problem is here really that our simulator, reservoir simulator, doesn't tell you if the response is transient or it is depletion, you know? And that is very important, because you could not underestimate transient response compared to the depletion response. Because, let's say, to explain why, because in the depletion response, you remember we talked about that. Depletion means I'm taking out something what has boundary. That is the volume which I know. In a transient, I don't have this boundary. So that means if I have a horizontal well here, it's very evident that I'm going to, in a short time, explore this with a certain drive mechanism. But if I have the well which is going to be like that, and I don't have any boundary, I know that it is a slab model, but this slab means this is cross-section. I don't have any boundary here and any boundary there. Then I have a huge pressure which is supporting my production from the side because it is infinite. So this is completely different response. That is why in this boundary mode, I am upward with the rate. The rate is slowly declining, and here it has a decline like that. See? Sharp decline. And here you have this. You see? And depending on the radius, this is going to decline further according to the radius. The bigger radius, less decline, normal. I have huge, more potential, more pressure to come. You see? Now you understand the first graph. This graph is must if you want to work in oil industry. You have always to use this graph. It will explain you simple everything. Otherwise, with all these software tools today, we are completely out. Why? We have a big problem. There are countries which has big data, and there are countries which has no data. Why Russians have brilliant mathematics and models and modeling? By the way, very many ideas came from Russia, including the first multilateral well, which they drilled a long time before anyone started to think about. But also because they didn't have enough data. So they concentrate to give mathematical solution. They made brilliant mathematics. But then they were impractical when it comes to the area that we move to the certain regions where we need to have also knowledge in order to explore more, because we don't have any more simple solution for many things which we are solving. Then we need to get more measurements, and that is why they failed. And today they all company in Russia exclusively using Western technology. And Brazil, which discovered oil later, you are very fortunate because you are getting, and I see that you are having now a very good program with Norwegians, best institute and universities, including Trondheim University, where I studied. I will say you will get a huge push that you will be leading power sooner or later. So I congratulate to all your efforts and the concept you have done. So then I would like to say that now comparing, let's say, analytical solution to reservoir simulation, it's not different. It is just complementary. When I want to make a screening study, that means first study. First, for example, you will see my next presentation. I got the data on Friday evening, and on Saturday morning, it was in one evening, I managed to get a study to perform. With the simulation model, you need to collect all the data. Here you have to presume that you have a mean value. That means some kind of the value which are reasonable to cope with, and then you are getting some out. So then I'm also putting that semi-analytical models can be used very efficiently to generate wellbore responses as a project screening tool. So that is basically the purpose of this presentation. And then the model description, I will then jump. First of all, the fluid is slightly compressible, liquid flow in multi-fractured well slab and box. If I use pseudo pressure, then I can use it for the gas, as I did it now. The fracture are conductive, infinite conductive uniform flux. We talk about that. Then fracture fully penetrated. That means if I have a layer like this, fully penetrated means that I have a height which is that height, if this is my well. But I may have only that as the height of the wellbore of the fracture, or that. You see, this is the height, but this here is a half length. So that is different, okay? And then the wells are either open or perforated. Okay, you can have here fracture, 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 and the wells can be here not open or open to the wellbore. So you can also simulate that. So these are very many particularities. And when we were developing software, we always had to contact those who are financing the project to provide us the input. So the most important is that we start with the slab model. Further, we use Laplace transform. We use green function. Then we use mathematical analysis and numerical techniques. to develop the solutions, to derive the solutions. And this is the, yesterday I discussed with you. You remember that I put that P multiply Q. No, the P is equal, the Q, no, that was my Q is from here equal P over B. Yeah. We have that the same expression, but it is this all is also here is set up that P is in Laplace space, by the way. So with this formula, we can solve a lot of things for, let's say, pressure, then we get rates, or rates, we get pressure. Okay? So numerical model, you will need to introduce an individual fracture rates, and for that you need n+1 equations. And the basic pressure equation for the system with n fracture are connected by the wellbore. That is the basic approach. Then you will see here, these are E, I, J, and K0. That's the Bessel function of the first and the second order. And BS is really this expression here. This is your BS. So if you relate pressure in a complex space, which is equal B, that is B, this expression, that is B of S. S is a complex variable, multiply Q in Laplace space. Then you're using for this expression, but in this case, we have, this is expression for n equal 4 for 4 fractures, okay? But when you put more and more fracture, you will have bigger and bigger expression, but that is why your computer will take more and more time to calculate whatever you, from the constant pressure, you calculate rate, from the rate, you constant pressure. So basically, in this case, we can say that we have well-test simulator, that is, we can change in a boundary condition from pressure to rates. What can be very useful. So you see BS becomes very long. Let's say for 10 fractures, formula for BS can have 8 pages. This was one row, 8 pages, full pages. However, by using smarter and more indirect methods, we may easily handle 50 to more fractures. And that was the benefit. We were very strong, you know, compared to our competitors. And crucial is treating the robust numerical approximation to the Bessel function and integrals and the Chebyshev polynomial. That is, again, Chebyshev was Russian mathematician, and that was combined by using Laplace inversion methods, okay? And again, at the end, we were using what is important to know, the inverse algorithm, and that was the Steffes, but it's supposed to work very fine. You will see later in my presentation what was not very well. So the beauty of analytical model is what? You need only not so many parameters. You need to describe model. Slab means I am talking about infinite acting transient model. Constant pressure in a boundary condition means I'm going to get rates. Outer boundary condition, no flow. If I put these conditions, then I'm going to have a box model. So this is going to give me depletion, and this is going to give me transient, okay? In a boundary condition. Oh, sorry. In a boundary condition, yes. But outer boundary condition, when I put no flow, then I am in the mode which is box, okay? So then we have here reservoir length in x and y direction. Usually I'm using Cartesian box model for that. Formation thickness, porosity, permeability, compressibility of the system initial reservoir pressure, viscosity of oil, viscosity, then formation volume factor, because I want to calculate the fluid volume in the reservoir, how much the fluid volume at the surface when it comes to the surface. So this is your surface volume, okay? Then fracture. Fracture is in how many fractures? How many I'm spacing fractures? So that means if I have here fracture, I want to know what is the space in between these fractures, okay? This is going to be 500 meters in this case, 500 meters. Then I want to know what is half length. So that is going to be this half length. Then I want to go, what is fracture width? So that means when I have width, okay, that means that I want to have propan fracture. Otherwise, I am injecting infinite conductive fracture, means injecting acid. I'm just cleaning fracture, but that means this fracture will close very soon. When I put propan, I construct like a corridor, which is firm, so it may last longer, but it costs 10 times more than another one. So you have to decide economically what is more efficient. Depend on your money. Very many companies, including Phillips Petroleum Company, that operate Ekofisk field, the biggest field in production in Norway, they just use acid fractures. They didn't want to invest in something what they don't trust that it will last long. Then well length, well diameter, yes. Then bottom hole flowing pressure, that is important because this is my inner boundary condition. And also it is, on one side it is that, but on another side it is going also to show, because we know that reservoir pressure decline like that, and then bottom hole pressure also declines. So we have to know that this, when I have a bottom hole pressure, here, B pressure to the wellhead pressure, I want to be sure that I have enough pressure to come here. So it cannot be a zero. You know, it has to have a certain limit. Okay? So with this, I'm able to and simulation. That is now when we set up everything, then we have only something relevant to the software. That is how many days we will run it and what is going to be the Steffes number. This Steffes number is very important because this is going to give us, if the system is very robust, I can play with this and then I get a very smooth function output without noisy data. You can see on my graphs some of the photos which shows us the result. So here is how this fracturing looks like. Now I have a model. The basic of the model was provided. I have here a vertical fracture well. In my run, I have also this, but also I have this fractured. These are the stages: 1, 2, 3, 4, 5, 6 stages. So I like to name it as a rate pressure time analysis because we usually talk about rate equals 0 when it's pressure time analysis, what we name as a well testing on. Here is the practically in short. These are my transversal fractures here, EF. And here is my longitudinal fracture, okay? So we have to, first of all, consider stresses. When we talk about how this is done, how we drill that. And then again, I'm repeating what we talk about, that you are perpendicular to the minimum horizontal stress. And now the infinite conductive fractures. We have that a planar crack penetrated by the well, propagate from a well by hydraulic fracturing with 0 pressure drop in the fracture during production. There is no pressure drop, okay? So finite conductive means the planar crack penetrated by a well propagate from a well by hydraulic fracturing with non-zero pressure drop in the fracture during production. And then FCD is the fracture conductivity. The dimensional fracture conductivity is defined as the ratio of the product of fracture permeability and fracture width over the product that is formation permeability and fracture half. So when I am going to summarize that, what I have here, I have here FCD, which is related to permeability and length. On one side, I have that fracture go to the well bore, and with this I have KF, which has dimension of L squared. This is going to be multiplied with omega. Omega has a fracture, the dimension L. Omega is the width of the fracture. So repeating once again, I have this, and I have, let's say, if this is my fracture, yes. So I have here the fracture width. This is my omega. And I have fracture permeability. So that means permeability inside that fracture. So I have permeability multiplied by omega, okay, on one side. On another side, I have permeability of the formation that is K here, the formation permeability, which is going to be multiplied by the formation KF. Okay, sorry. This is going to be KF, formation permeability, okay, multiply by the LF. And LF is going to be this number here. So formation K is not very big number, but LF is big number, okay? So I have this. On another side, I have here, omega is a very small number, but KF permeability is a huge number because it's finite conductive. So it is really huge number. It can be 100,000 or millidarcy. It's a big number. So the most important here is that we know that at the end I should have dimensionless number because I have L squared multiplied L is L on third divided by L on third. And that is my LCD, which is no dimension 1 or no dimension. So FCD is dimensionless number. That is the most important. Okay? So now we have different fracture orientation. We know that. This is longitudinal, this is transversal fracture. We have spacing here. We don't have here spacing because there is one fracture. Here I have spacing in between fractures. We also talk about this length has the meaning that this should produce ideally on the long time the same as this one here. Okay, so now I got a case when I have a real data from the field in North Sea, UK sector, when we operated. I have to estimate optimal number of fractures. I have to target that the production is 1 million cubic meter. I have also 8 fracs. And to assess the productivity of creating fracture, I have to demonstrate that. And I have to detect the difference in fracture production for propan fracs and for acid. So you see, and at the end, I want to first give results. Yes, we did we decided that this is 8 fracs the sufficient to give us production, because so that means I have a well, I can have 1, 2, 3, 4, 5, 6, 7, 8 fracs. Any new fracs will not bring me more. How did that? That means my cumulative from 8 fracs is like that. For any more fracs, I will be like this, like that. And this is going to be my capital, and this capital will not cover the cost of these new fracs. So that is why we cut it out, okay? So of course we need to get more data, and this is more study. So this is done with a certain software which is named How If. It is how if I have 5 fracture or 7 fracture. That was the idea of the name. In UK, this is the real case. And here we have ideally fractures are not so ideal. They look differently along the path. Even, you know, you see the well is not ideal. We have to improvise everything. Improvise in the sense that we put the tower line is like that. And then I put in average the length of the half length, or the height even of the fracture. So I can, and then I can make the averaging here, but also averaging at the half length. So with this, I'm able to create the pretty similar system just in order to get in a few hours the results, or even I will say in less than 2 minutes. So this is done with the finance of BP ConocoPhillips, NFR Research Council and Institute where I worked. And I met in that time Raghavan, Bijan, Rigatos, Viggo Holm. He gave us the first money. Then Raghavan, I have to face 3 times, and he's the very famous guy. He made the book probably in well testing, one of the leading book, Raj Raghavan. And you can see all his solutions are mentioned, including the one I presented recently. Martin Lawrence, he knew immediately from before, so he was the very, very favorable to our work. Then Chris Dyke was also, and Bill Landrum was also the guy who contributed. And then I was given data from Amerada Hess, and also data from Leif Larsen in Statoil, who managed to be my opponent when I was defending my PhD. He's a very good mathematician, maybe one of the leading in well testing, and he's developing Sapphire software in well testing. So we have, this is my ideal case. I have estimated height of the well and half length. And then of course I have a reservoir, which is a certain height. And this is what I have. Each fracture has a height, half length, and omega, that is this part here. This part here is omega, okay? So now I have wellbore data to put in, fracture data to put in, reservoir data to put in, you see? And then that is the model. You have to put up this, it's quite nice, and it has much more feature that I'm presenting just now. I'm simplifying. It can be the length of can be equal, unequal, the half length. So I can have this, that I can have half length like that, or like that, or like that, or like that, or like that. Okay. Or then also penetration. I can also have this, the height, different. And then also I can have the fracture not equally distanced, unequally distanced. It can be like this or like that. See? So with all this you can, and then also I can include the choking effect. We talk about that I can include this extra pressure drop due to the pressure. This is here. And then I can have here full-time solution, or I can have early time solution. Depends if you want to move to well testing or late time solution. Then I can include wellbore friction in addition to that, because we know that when I have very many fractures, this friction is here very dominant. So this profile is not equal as we saw there. You remember that we have a drawing here. That means that this here means that I have a huge pressure drop at this point. This pressure drop is not going to lift me more oil out. So this is, and then these are the reservoir parameters, fluid parameters, only viscosity, formation, volume factor. Formation volume factor is only one factor which tells me, okay, from the reservoir, this is the volume I want to lift up to the certain volume at the surface. So that means from reservoir condition, I can be in the surface condition, which I have to report for my economy analysis. And here was the question, how many fracs? So here what we did, we made 10 fracs, so I did it. So first frac produced this quantity, the second add this, the third this, the fourth this, the sixth this, 7 this, 8 this, 9 this, 10, and 9, and 10, there is nothing to come. So I made a cut at this point. I said, I excluded this, and that is going to be my, and you see my rate is the same. 9 and 10 rates are not bringing anything in money. So this is excluded when I'm plotting cumulative at a certain time. And this productivity index, again, here, I'm not productive here anymore. And this is, you can see here from the benefit cumulative gas, this is not going to pay me any fracturing. I need with this amount, I have to pay this fracture and this fracture. With this amount here, above the line, this line, I have to pay only that fracture. This is out. So in percentage, I can see I made a cut when I'm not receiving any more cumulative production than 2%, up to 1.8%, and when I'm below that, and that was number 9 and 10, I just exclude that. So with this, I managed to finish that this is the best scenario, to have 8 fracs, and that is really what really proved this concept. Then I can make income from each of these fracs. You can see here how the income, you can go to an economy. To be honest, I'm not very fond of economy, so I will not discuss that. But here, this is what your management want to see. You have to see the certain cost of the fracking, and then how much you will be earning with this, what you're doing. Of course, you have to set up certain criteria. One criteria was 1 million cubic meter per day. That was really from reality. And then you can see here, that was very good that I have this plot here, that here, when you see I'm plotting cumulative rate, this is my cumulative rate. I'm plotting here the rates 1 and 8, then it's 2 and 7. Here are practically two overlapped curves. Then it is that is 2, 3, and 6, and finally 2 and 4, 2 and 5, 2 and 5. So as I see here, I have this, because why? Because when I have here 1, 2, 3, 4, 5, 6, 7. What I have here, that this is my biggest drainage radius, and this is my drainage radius. This one and this one, and then this one and this one, and this one and this one. So what I can find out, that this, which are in ideal conditions, when I don't include all other pressure drops, are equal at the edge. That is the most productive. That is at the top. Then I have this, which is going to go slightly lower. Then this one is going to be pretty lower, and this one also as well. So you see here that this one here is this here, and this here is the one at the bottom. This here. So this is also for you to understand. Whenever you have a simulator, try to make this model to know these people are doing interference in between fracture. So that is the full solution. Or they are cheating you. They are putting on the line formulas to calculate something from the literature. This is very first term. You have to have this variation here. Without that, you immediately you can make a QC of the quality of the simulation. And I will tell you, if you want to do that with reservoir simulation, why? Because here I have transient response. This is that response here from the Fetkovich guy. When I meet the boundary, I am in this response. When I have here, I have a transient response. This means I'm draining small, and this means I'm draining big reservoir. You see, the decline is very small in pressure. Here, in rate, decline in rate is huge because the drainage, the radius is small. So this is a really nice understanding what is going on. So with this, this was my, so you see, this is the what I told you, 1, 2, 3, 4. So this is really, you can see here, this is the biggest one. Then these two here are this one, then these two here, and that one, and finally this last one and this lowest one. If this means I have honored in the simulator interference in between fracture. And this is for the finite conductive fracture, which is the solutions are very complicated, believe me. So this is really now at a certain, my cumulative production after 1500 days, that is about 4 or 5 years, to see that I have the same production for these 2 points. This is 1 and 8 production. Then I have, you see, 2 and 7. Then I have 3 and 6. And then I have 4 and 5. So I'm pleased because this is really what is correct. See, it is. So this is now, then the rates, then also here, I don't want to spend too much time with this. When we have 3 proper and finite conductive fracture, then you have also cumulative, and then you have, that means you will have, with 3 fracture, you will have these 2 are the same, so you have only 2 responses. The biggest one is 1 and 3. This in the middle is squeezed. There is no drainage here. Here is a big drainage, and here is the very big drainage. So that shows also that you are honoring. And then here is, okay, then cumulative, it's not important further. And then this is important. We talk about the finite conductive fracture. Finite conductive fracture is fracture which has the volume. So this is your omega, this is your height, and this is your half length. So this, of course, volume means that I can, through this volume, produce more, okay? So this honor that red one. On another side, acid fracs, is like this, you see? So I don't have omega, and I don't have, so you see, this is the difference in between propant volume and acid solutions, you see? Because it is a plane and you are just, you know, flowing, you're collecting your flow. to the fracture from both sides. Then through the fracture, it goes inside into this. But it is a huge pressure drop here, you see? And that is why you have this. Of course, it will be different if I don't have this, if I put that my well is longitudinal, and it will be, a fracture is longitudinal. And here you have that you are producing from the, let's say, fracs, which is going to be like that. You see? So this is going to give you much more oil out. Then this. So this is just all nothing. Final comments. Study results may be used better estimation understanding of fractured well. Obtain results has a verify, okay? And of course, we need to introduce PLT data. PLT data will be data when you have a well and you produce these fractures. Up to now, I model it, that they really measure these rates. You see? Rates fracture 1, rates fracture 2, rate fracture 3, and then I'm very confident that this is, then I can make a history match on my fracs, and then I can make a predictive model. This is thanks, I am thankful to Amerada Hes and to Valhall data, which I got later. Okay, this is really what happened. Look at this. What happened with one of my solution, that is this solution here. You see, my Steffes completely exploded. So I'm now converting, I have rate, and I have complex variable S. But what I have to get here, I have to get rate and time from S. From this S, I have to convert from Laplace space, because in Laplace space, and here's my real space. In Laplace space, I have only one unknown, so I have fast solutions. Instead of time, I put that it is a complex variable, which you don't solve, this complex space. So now I convert that by using Steffes algorithm, S algorithm, or program, to bring me T time back. So from here, from Q time, I move to this here, and then through Steffes, I'll go back to CAM time. So time, first I remove to get the S. From time I go to S, and then from S I go back to time. I can go back to time. I go back to time by using Steffes algorithm. Okay? And this exploded in this fracture 9, you see? So that can happen. Okay, so then one more. Do we have lunch now, or how it is? Hello?
I think it's good.
Do you think it's a lunchtime, or we continue? What is your opinion?
We can have a break.
We far from the lunchtime, but I think we can take a break for.
Yes, okay. 15 minutes break. Is it okay?
I think so.
No, but do you need to go to lunch or not?
Not now. The lunch,
Okay.
I think 1-2 hours for now. So
Okay, so we have 15 minutes break then. Is it 15 minutes break?
okay.
Okay, thank you. Adriana, is the break is finished? Can we continue?
Yes, we can continue.
Okay, thanks. So, okay, let me see now where I started. Just a moment. You can see my screen, I hope, yes or not?
No yet.
Not yet. Oh, okay, I didn't share my screen. Okay, let me see now. How should I do that? Present now. Entire screen. Yes.
Yes, okay.
Yes, okay. So now, so we finish this part here. And we came to this one here. So here, this is once again the, can you see my screen, please, now?
Yes, we can see.
Okay, so as you see here, this is, I think this is chalk, by the way, and in France, this is naturally fractured reservoir, and usually you have to position your well. The well is not always ideally horizontal, it's undulating, it goes up and down, and these are the fractures. I put circular fractures. We anyhow never know what is the shape of the fracture without microseismicity. So here, what do you think, what is this? What do you think? What is this? This is, believe or not, a field in Halvdan, on which I worked 3 years ago or 4 years ago. And it has about 60 fractures. All fractures are horizontal. All fractures are horizontal. And each fracture has, each horizontal has certain fractures, you see? You see that? So each of these fracture looks like that. So when what was the name of the person the gentleman which asked me yesterday about the CO2 injection? Is he present today?
Yeah, it's me.
Oh, okay. And what is your name once again, please?
It's Andre.
Andre. Okay, Andre. Andre, now I was thinking how to answer you, so I will now answer. So let's see, let's say only one thing I have to a bit. Okay, so here is what was my problem. I have two wells. This one, okay, it's not like that. And another one, I will put in another color that I explain what I did. I have two wells, and then I had another one, which was producer. And so this well was to produce oil. And this one, this below well, was to inject water. No, gas, inject gas, sorry. So we were here. It is like this. Okay, excellent. So I can then use this. I can now, so one is producer and another one is injector of hydrocarbon, let's say hydrocarbon injector. So I can here put, see here, just, I will put it that it is injecting whatever is. So this is injector. So what I was given this part only where I have something what I'm injecting here. That means I'm injecting in this plane, which is my fluid, and I have to find out what is my recovery. So a recovery will be NP, that is produced oil, regarding the volume of oil. So in this here, the whole box has volume of oil, and NP is how much I recovered. So let's say that is what I'm always saying. Recovery of this would be, if this is my NP, if this is my volume, NP will be how much I produce, and it is going to give me recovery. Okay. So what I have to do then, I then have to do the following. I did the following. I use Buckley-Leverett theory and I use certain knowledge which I gained before. When I have a relative permeability curves for multi-phase flow, then I can calculate water cut, which is water over water plus oil, or gas cut, which is gas or gas plus oil, yes. So this is water cut, and this is gas cut. So in order to do that, you have to know a little bit about the Buckley-Leverett model. And you practically have to have, first of all, relative permeability curves. If it is oil and gas, if you're injecting CO2, you have to have such relative permeability curves, that is relative gas and relative oil. And then you have to set up the Buckley-Leverett model. Buckley-Leverett model will give you the flow cut curve, which is your water cut, or oil cut, or gas cut, and at that point, and you have to find out your gas cut and plot it versus saturation of gas. This tangent here is give you the recovery of your gas, which is pushing oil, at the first breakthrough. So let's say if this is your model and you are injecting gas here, the question is how much I am recovering when I have the first gas moving on. Because here is going to be like this. This is pushing oil. This is pushing oil. And finally, I'm getting the oil. And finally, here with oil, I'm getting the first gas. So my efficiency is, of course, if this is upper, not lower, let's say. So with this, and then afterwards, you can add a little bit more injection, and then we will get the final recovery here. Here is going to be the recovery line. That is the model given. So with this model, simply analytically, you're able to calculate what is your efficiency of gas injection, or you can also try to make what is your oil injection and see are you efficient and how much, before you go to any reservoir simulation. So this is my answer to you, what I wanted to discuss with you and to show how you can make analytically something without having this fancy mathematical model. Okay? or simulated. So this is, as you see, this was my project, and that is, you see how this is complex. You see, you have this model with these wells, a drill. They are looking like multilateral, but they are not multilateral. They are horizontal multi-fractured wells. At each of these lines, you have about 24 to 30 fractures, and it is amazing how they are producing that. So here I just wanted to extend that I was also inspired. This is the model we discussed. We went through all this. And here I'm getting another. These are also a lot of, here what is important that I see the difference when I'm changing the inner boundary lasting conditions. I'm changing conditions. I'm setting 3 different rates, constant rates. This is constant rate 1, 2, and 3. And then I'm getting these peaks, you see? And then I'm simulating infinite conductive fracture and finite red fracture, see? So you can see that the red is much lower for the, in this case. And then here we have the observed cumulative. I have this for 10 years run, and you see that this is my setup, which is telling me that the fracture are closing. You see, I have here fracture. I have that that my fracture R has different wells, half lengths. So it has, let's say, 36, 34, and 20. So let's say it is 20, then it's 36, no, then it's 34, and then it's 36, this one here. Let's say. So I can see here that here I do match this fracture here, length. Then here until here, I do match this. And then, no, sorry. Until here, okay, I will repeat once again. This is my 3-6. This is going to be my 3-4. And from here on, I am going to be at fracture 20. So what I can see that with the time, why my fracture is reduced from here to here, and then from here to here, from this model. See? So that means my fracture need to be refractured. I have to make a re-stimulation. With fracturing, I need to move this fracture boundary gain efficiency more on both sides. You know, so then with this, so with this, you see, I have this, and then I have this here, you see? And from this here, I have this, you understand? So basically, with the time, fracture will close, and then we have to reopen the fracture. That is the whole study about. And then here, what I have also possibility that I can move from one inner boundary condition to another inner boundary condition. This is known usually as a superposition. So that means I can first have inner boundary condition of constant rate, which is give me the pressure response. Then I have inner boundary condition of constant pressure, which is going to give me rate response. So I can simulate my model completely. Here is another South-Arne field, which also I get from Amered de Hess. In this field, I have another, what I'm also only looking at the productivity index when it's 50, 15, 2.5. And then I can also see that with the time, I'm moving from the stem which is 50 Darcy to the 15 Darcy, and then further for the 2.5 million Darcy. So the Darcy is, this is the huge number. You don't have such a field. You have millidarcy. Darcy is fracture permeability. So that is a fully propan fracture, which has different permeability of this. So with this, you are going to be like that. You are going to be like that. And then finally, you're going to be like that. So you see, finally matches this here. So that means you lost. Something is going on with the fracture. The fracture might be from being so wide, it starts to be very narrow, or I have a huge pressure drop that I have only permeability 2.5, but here I used to have permeability 50. So this 50 is the stem, which is the top one, and this 2.5 is the stem, which is the bottom one. So my real data are coming here to this point here, and then I have to do something with the fracture. I have to clean it. So this is the, and then also I can easily make different steps, and with a different step in a boundary condition. From one constant, I get this response, but if I want to ideally match all this, I need to put very many constant rate steps, and then I will finally get a better and better match. That is what your simulator is doing, but you don't see that. So then here I'm now, instead of doing, I'm also doing, this is constant rate in a boundary condition, and then you have pressure response, and then I have constant pressure, and then I have rate response. And here I have something which is relevant to lay time approximation. There's some analytical solutions, but this is important to understand for you. Why this is important? Because I'm trying to emulate horizontal well with two fractures and to measure how it will be emulated by having one vertical well with a huge radius. So then I'm comparing my model, analytical, with this vertical well model. And I'm pretty close. If it will be longer, more than I will have ideal match at the end. Then here, I have 3 fractures and I have half length. And with this half length, I have let's say, first of all, transversal fracture. And here I have a big pressure drop. I have the same half length of the 3 longitudinal fracture. So I have 3 longitudinal fracture. And then I simulate what is my rate of this, not each fracture, but a well with a fracture. Here, I have the solutions are much closer. Why? Because I don't have a pressure drop here, you see? In this case here, I have this fracture, but it has like this connectivity. This fracture has like this connectivity, and the third fracture has like the connectivity like that. I have a huge pressure delta P. That is why you can see the difference is huge. It's maybe 5 times bigger than this one here. See? So transversal fracture has a problem of choking. You see that we talk. So I have this, that here I have a huge pressure drop because by coming to the well, I'm losing a lot of pressure. And here I'm not losing so much pressure. It's not to say I'm here open to the fracture like this. So there is this very small pressure drop. So that is what I wanted to share with you. Okay, and then that is another issue that was relevant to the previous day. I can here inject rate or water. And this is my simulation of water, but I have here only one constant in a boundary condition. In this case, I'm injecting water and I'm not producing, and I'm making history match on injection of water by keeping pressure. If I will have several steps, I will get very perfect match. But now with this, I'm not getting very perfect match because I just put one value of the inner boundary condition of constant pressure. So this is all that we have: slab model and box model. It is transient and then depletion. And then, of course, once you have a simulation to the model, you can easily use such a tool for very fast simulation. So you have just to make that can be Monte Carlo simulation. You will have reservoir data, fracture data, and well data, and then you have to make a certain number of fractures, and then you have to make variation of each input parameters. We know that we have fracture parameters, horizontal well parameters, and reservoir parameters. You list those parameters whom you don't trust. You make certain distribution, and here is the distribution of reservoir data, then distribution of fracture data and well data. I make simulation. I made about, I don't know, 2,000 runs. And then by doing that, I want to make distribution of the, let's say, each parameter that it has low, mean, and high value. It's like triangular model. And based on that, you have the whole optimization process. That is what is risking analysis today make for you. So the next, that is now, I was doing the reservoir simulation or history match of the parameters, and then I can make the proper distribution of the properties. Now the next one is, can I now make the link to the from the reservoir? I want to simulate from the reservoir up to the top of the to the surface when there's when I have a lot of pipeline. Because you know that once you have a well, you have another well which produce, and then you have a third well. So you have a lot of pipeline to flow until you don't get data separated. So with this, you want to make flow simulation from the reservoir to the flow simulation to the network. And this process is very ideal for that. That is how it looks like. So you are really, in each delta T, you are connecting the reservoir model. In each delta T, you are transferring pressure. These are the reservoir pressure and saturation to the network pressure and saturation. And that is how you are getting final flow, but having the whole conceptual model. Today, Eclipse uses software gap from PETEX. And at the university, we have also this material balance and PETEX, so we can make such a compiled model and then we simulate it. And then in addition to that, finally, the economy comes. So you have to include the cash flow, and then you have finally to make the overall network simulation with the, if you want to change steady state simulator pipeline to the transient, you have to include Olga simulator. So these are based regarding fracture design, fracture geometry, leak off, fluid rheology, prop and transportations are important. And then design model requirement is that you understand the basic physics. You have to predict the job results and to provide decision-making capability. And you have a model which is including tension, sliding shear, tearing shear. So, and then you have very many models now. I'm here talking how I am creating the fracture along the well. So these are all models which we have to consider. For that, your mechanical engineering and knowledge is very welcome, because you can easily understand PPK, 2D PPK model, 3D MFRAC, STEAM, FRAC. You see, these are the all models which will help you that you make screening analysis without having sophisticated and very expensive numerical simulator as Eclipse or Intersect now. So these are all what I wanted to say. You have to consider fracture Weber orientation, Weber configuration, reservoir acid solubility. Multiple fracs can occur when the perforated interval exceed, or that is the connection with the theta and the radius of the well. That four radius of the well. If this is radius of the well, then four such radius, four. The exceed then you get a perforated interval of four these wells, the radiuses. So these are then well orientation, and here is also about longitudinal fracture. I mentioned that before. So this is also how this is related to the stresses. And practically this is all what I wanted to discuss with you today, because this is more to the construction of the fractures, which is not the purpose of my presentation. Here I put all my publications, which are pretty were present, because in the time when we started, this was something new, and this model was pretty well done and among the leading one. So now I will only make the one more study, which is going to be by reservoir simulation. I have a fracture reservoir, and the question is here, I have a simulator, it has multilateral simulation, vertical, deviated, horizontal, multi-fractured wells. For multilateral one, you can easily create in this simulator, but I will also show you what I did with multilateral in the coming presentation with this Eclipse simulator. Here, what is very important is that we have a conceptual model. First, you make a screening analysis. You make choice of the following. You have vertical well with one frac, horizontal well, and multi-frac well, okay? And that is same in each of the study, and each of the study has what? Different permeability, K in millidarcy. Here is 1, here is 0.1, here is 0.1, and here is 0.1. You see? So divide each time from 1 to 0.1 by 10. So this is 1, this is 0.1, this is 0.1, and this is 0.1. So here it is divided by 10, by 100, and by 1000 permeability. Okay. So now I will say cumulative production after 15 years. How much is, and cumulative production after 15 years when I have 1 by 1 kilometer or 2 by 2 kilometers. So I will have to digest and put all these results in a summary table. Here is all how it was done. I'm just jumping out because we're out of time. Otherwise, it's not the purpose that you... So with this, you start with the simplicity, and then you come to the model, which is going to give you the summary. And when it has here, I have here 1. You see here, 1, there is not so much difference in between for 1 millidarcy, yes, but for 0.1 millidarcy, I have variation. Look at this. For point 1, I have also variation, and here I have even more variation. So surprisingly, the biggest contribution for multi-fractured horizontal well compared to other wells is when I have this ratio, when I have 2 by 2 kilometers, and then I'm getting about 4 millions for BCM for BCM to this would be the gas injection, the gas production, 4 BCM. So here is 4, here is 5, but this 4 is much different than when I consider how much vertical well produces, how much one frac vertical well produces, or horizontal well. So horizontal well is out and vertical out. So interesting is only to consider here a vertical well fracture, 2 mile. And then here I have that I'm here in this one, I'm here equal, you see? So that is, one is how large is the area, and the next is how large, what is the permeability. So basically what I'm considering here is the permeability, but also I'm considering how big is the area. Is it small or it is big, twice big? So this is 4 square kilometers, and here is 2 square kilometers. No, 1 by 1 square kilometer. So by having 4 times bigger, what I'm gaining or losing, okay? And you see here that I'm not efficient at all. So the only one is this one here. Look at this. So that is interesting. This is not so much interesting. Okay. So now we are going to the next stage, which is multilateral theory and flow modeling. So we have a small introduction to this software, which I presented recently, is also able to give you the production, how we are comparing multi-fractured well with vertical well, vertical fractured well, horizontal and multilateral. So we now learn that from that we have to consider to make a simulation, semi-analytical model, or we can use then move to the flow simulation by using finite differences. That is Eclipse model, for example, or CMG, and then we can find out which results are the best one. Okay, then we have here multilateral well theory and flow modeling, multilateral well flow simulation with Eclipse. I will talk about that. I will talk about huge multilateral well. When I was a project manager in Schlumberger of EOR in Moscow, Schlumberger Moscow Research, where I lived 1 year, I got horizontal well to make the project and to lead that project. And instead of putting fractures, we decided to do the following. I was asked, because Schlumberger in that time used to have special drilling devices where it can make drilling for the very many laterals. So we created the model of horizontal well with 400 laterals. 400, can you imagine that? And then we wanted to investigate that model in very many reservoirs, okay? So that was one of the projects I managed to be working with. And I'm going to show you only some of the results which we use for the vertical fracture, well, not for the horizontal. Some of them are confidential. So multilateral, what are multilateral? They are not new. multilateral technology is not new, and then we are copying really this. This is multilateral draining from the mother nature, that is our tree, and we are emulating that. The first work was done by Russians, by the way, and then further in the United States they also tried to contribute in 31 and 38. And here is we go to the petroleum engineer called Alexander Grigoryan from Azerbaijan, who constructed one of the world first documented multilateral well with 9 lateral. You see, this is his model in Bashkiria. And they managed to increase the exposure to the reservoir 5.5 times. And they increased production for 17 times. And here today we have different laterals. We have 3 laterals like this, then stacked 3 laterals per layer. Then we make like this. So it is amazing technology, to be honest. You can also penetrate the fault. There is no flow here. This is like a plane. There is no connection. Then you drill it and you come to this here region. Otherwise, you cannot that you have to move your platform with the vertical well here and then to drill it and then to perforate. But here we have a horizontal well. So this is quite, and also here is another fault. So this is also like a plane without connection. So you can just move to another box and to drill. So you have now 3 boxes, box 1, box 2, box 3, and then you have that you are drilling from the second box in the box 1 and box 3. Then you can have also this one, then you have injector, but then you can have that you are producing water, so the water will come probably like that, but because this is going to be produced somehow, you are probably keeping this water wave propagation, you are slow down that. So this is going to be produced from here, and also from here you are in the same time producing oil. The question is now how you are separated. So then you are always, why you are doing multilaterals, you have to reduce number of slots and then also number of platforms for drilling and number of Christmas trees, and then you reduce number of casing, less casing, liners, cemented, reduce the volume of cuttings to handle, transportation, and so on. So basically it is a functionality. And then multilateral drivers. When can multilateral be used? Small pools, small areas, compartment, which we presented. Then pools impossible to connect with the one hole, that is also what we presented. And we want to achieve maximum reservoir contact and extreme reservoir, and maybe even extreme reservoir contact. So see, this is and then you see this is the overall workflow that you include use of less slots, increase reservoir contact per well, that is what must. You have to access small pools, then generate less cuttings, and then reduce cost for casing and cementing, reduce cost using fewer wellheads, subsea trees, use as an injector post-economic production, and use existing wells and add laterals. That is the most important. So as you see here, that is why we are doing, and here when I have a main wellbore, I have dual opposed laterals. So one is exploring here, another one is here. Then I have here vertical, and then I'm exposing also there, but also in another box here. So it is amazing what you can do with the multilateral. So now I'm presenting my study case. You see, this is multilateral flow REN with eclipse Schlumberger simulation. You know, screening analysis of factors that could have significant effect on the prediction of a well with laterals performance, well with laterals arrangement. Partly reservoir is different because what you can target differentiation in heterogeneity. Then you can handle different fluids differently. And then you can also include wellbore friction and water influx. So it is a lot of possibility. It is like making a new musical instrument. You are playing the music with that. So this is my well with laterals. Here I have to include fluid, heterogeneity, and water influx. And here is my vertical well with 1, 3, and 6 laterals. You see? And then I have here different realization. Here is the script we did to create lateral scenario. We put that, imported that into Petrellari. From that, we made a simulation model. So you can see the different cumulative oil productions. And you see definitely that the vertical well with 6, that is blue one, is the leading one. Of course, you have very many laterals. Yes. That is light oil, permeability K, how they did with the light oil. So I can now change permeability 0.1, 0.01, 10, and so on. And then I can also plot the differentiation in between cumulative oil and oil production. Then I can also introduce KV, KH. KV, KH, if you have a reservoir, this is your KH, horizontal, and this is your KV, vertical. So KH is horizontal in X or Y direction, that is KH. But I'm now putting KV that I have 1, that means this is 1 and this is 1, so I have a homogeneous case, and this is some kind of heterogeneity. And then I can see what is the difference when I have 3 lateral well. So I'm producing, I have 1 well production with 3 laterals. And then I'm considering 2 scenarios for KV, KH. Sorry, of 0.1 and 1. See? And then also with viscosity, I can see how viscosity changes that. You see, this is nice. See that here I have more viscous or less viscous, okay? That is also how I'm going to be receiving different results. And then I can also put fluid viscous oil is now, and then I also introduce KOKV. Then light oil, so I can change from through different reservoirs. Light oil, what is the difference? Then I have multi-segmented well. Multi-segmented well means that I can have pressure drop calculated in segments continuously, and introducing that, then I'm looking at multi-segmented well for K equal 1 permeability. And then I see that there is a small differentiation in between perforated and MS perforated well, or even open hole. There is a small one. So that is how you can make, after such analysis, you can come to your boss and say, there is no reason for us to do that. My suggestion is just cancel it. Cancel the most expensive scenario, that is in this case probably multilateral, multi-segmented well, because I don't need to use a long time simulation. So that is, here is also our trial, not mine one, but some colleagues, they wanted to introduce the analytical simulation. With this simulation, they also try to make analytical model, which is going to simulate the flow. So they have to have the flow in the first pipe, it's 3 lateral, and then third one, and then they combine, and then finally they will get the pressure drop in the laterals, and then they will get the pressure drop overall in the system due to this vertical well with 3 laterals. So this is what I wanted to say. Here we can also introduce the so-called equivalent Weber radius. We learned that what I'm trying to say by having this radius, which is like this, I'm going to increase that by having 3 lateral wells. So that means I have here RW multiply with E over minus S. And that is going to change my radius due to that I'm now more exploring, and because I have a huge drainage radius. Here are all scenarios we did for all kind of the multilaterals. Pretty impressive study. And at the end, particularly this is very interesting because you put in a certain like 5, and then you want to see how you can drain mostly your reservoir. And finally, I would like to see, we decided to make this realization of the horizontal well with 400 laterals along the horizontal well. These laterals were also going like this, like that, or like that, in different, so that means when you make a cross section, it was like this, let's say, and then you have here like that. So with this, this is somehow enlarged, yes. So what is important finally to say? It is important to use screening facility as we did with the software multi-fractured horizontal well, or screening with whatever tool you have, including semi-analytical when you are screening multilateral. But you need first to put scenario that you are testing something. When it's tested, you want to go more detail in a very detailed study, and you know now that among everything what you should choose based on the pre-screening study, and then that is how you are most efficiently going to finish your study. Okay. So here is my coning when I have a well like this. And you will have here coning, let's say like this. And the question is here, when I have inflow like that, how in a hell this horizontal well with lateral response is going to look like? You see, is it going to be like here or something different? So, so here now I am going to use the horizontal well with 9 laterals in a very simplified model. That is my study with Eclipse, which I did, I think, last night. So here what I did, I put a horizontal well, I put laterals. This is going to be like we did before, I'm putting 9 laterals. Along the horizontal well, and then I want to see what is my production. Not per laterals, but I'm just interested to see what is my production. And here you can see that pressure and gas production rate. So you can see here that I have gas production rate, and also I have a pressure here. And then also what else I have? I have oil production, and I don't have any water production. Water production is 0. Then I have oil production, which is, and water production. Water production is 0. I have oil and gas production. So oil production is green, and gas production is red. And brown is my pressure. Here I can only make my both cumulative production and the rate production of one horizontal well with 9 laterals. Here I'm going to show also that, but including my pressure. Here is just the same. And then I'm comparing gas production with liquid or rate production of oil. So basically this is then when I want to see the region, I want to look at the region, how it looks like. I'm not plotting here as well, but I see how the changes of pressure looks like at the end of gas saturation, of oil saturation, and then of water saturation. And here is this model, and here are different like gas saturation at certain time. Okay. So here is, are there any question now? Hello? Hello?
We are here.
Do you have any questions now?
No.
What we are talking now is really, we start yesterday that you understand. Yesterday we spent a long time to understand how your system respond once you start producing. So it is not that you just put the well in the reservoir and you start producing it. It is the question how your system respond. So you have, in order to make the system respond analysis, you have to first define system input, and then you have to define what is your system output, okay? Then you have to use previous knowledge accumulated that this output, input and output responses in rate or pressures can be used for interpretation of reservoir in a sense that you characterize reservoir by defining your volume in place, your skin, your permeability, your drainage radius. Now we move to more complex well, horizontal well, which are more productive. Then we move to more complex scenario by having horizontal well and multi-fractured horizontal well. We emphasize very much to the fracture conductivity, like infinite conductive fractures, finite conductive fractures, or uniform flux fractures. Each of these fractures are really defining the area in between two planes. They are more productive if we inject propan. So we have a propan with a fracture which has so-called omega, or the width of the fracture. If we don't have propan, then it's acid. We are just cleaning fracture, but it's going to be closed very soon. And then we move further to multilateral. Multi-fractured and multilateral are top today. Why? We are because that is why United States is not dependent anymore on the gas. When you're talking on the shale gas production, tight gas production, they're leading power in that. So with this knowledge, by having new technology in design of the wellbore, we were able to move from the conventional reservoir to unconventional reservoir, which are tight gas, shale gas, tight oil reservoir, and even further to naturally fractured reservoir. I promised to give you also short introduction to naturally fractured reservoirs, maybe because this is also very important. Why? Because, and also, okay, we went through the case of of multi-phase flowing, and then we also talk about different. This is the FMB, flowing material balance. We talk about that. I don't want to spend your time now. You are too tired for that. The most important that you know that you want to come to this point here. This point here is going to give you gas in place or oil in place. And of course, this has to be expanded, this formula here, for the multi-phase flow. And we also emphasized yesterday what is the meaning of multi-phase flow. How that is done, we are using FMB on such a way that we plot here productivity index, and with this we are able to get volume in place. So that is all what I wanted to share. FMB, here is the example. You see here I have productivity index, that is this, right, and it has to be straight line. When I have this straight line, I need to match rates. These are rates here, and this rates match is going to give me my oil production. That is oil initially in place. We name it all like this: oil initially in place, or EEP, EEPI. So this here I have plotted also. Then I can also introduce the multi-phase flow as it is now. And with this multi-phase flow, I can see that my volume is somewhere here. But then with the single flow, it will be smaller. Then here we also went through all this, that I use type curve. From type curve, I move to, here I construct my well bore, and then I have my production data. I have my static pressure data. In this case, I don't have any well test data, so I don't have it. And then I after having the type curves, I create analytical study, and then I move to the numerical model study. So as you see here, we have a long time to go. And with all this, the whole purpose is at the end to come to the predictive model and forecast model, which is going to give, for, let's say in this case, I choose 10 years, what is going to be my predictive rate. So all this is massage of the data. I'm doing that in order to get knowledge on your reservoir. You have to repeat, and each time with each new data, you are repeating the processes to renew the data knowledge of your reservoir, okay? So now, let me see what else I would like to show you. That now you have enough listening to me. Adriana, oh my God, what this guy is talking about. Okay, so let me now show you the real world. Okay, you see, this is the simulator. Can you see it? No, you could not see it. Can you see it now?
Yes.
Let me see that I have the white behind, so I don't have anything. No. Sorry for that. Okay, just a moment. I'm trying to find one white window, so you're not you don't have this overlap. Yes, okay, this one can be good. Okay. You see, the beauty of the semi-analytical model, you look at this. You have here, I want to move from here, from 15 fractures, which I have here, to, I will name it, I want to do the following. I want to make, let's say that I want to make 40 fractures, okay? 40 fractures. Then I save it. Okay. Then I have, of course, to increase number of fractures to 40. Okay. What I have here, I have slab model. We know that is a transient solution. I need to get longitudinal transversal fracture. Okay, I run it like that. I have well, which is 1,000 meter, but I will put 3,000 meter. Okay, 3,000 meter. Okay. When I put 3,000 meter, I will get some kind of the results, how much I have to make. 3,000 divided by 40 is going to be like 300 divided by 4. That is going to be 60 meter in between each fracture. So each fracture is 60 meter. Distance in between fractures is 60 meter. So then, when that is done, what else I need to get? Okay, the half length is 25 meter. Let's say that I put 50 meter. 50 meter. Then I put height of the reservoir, that it is probably bigger, it's 200, let's say. Then here I have to put that I start from now. I want to have it for 10,000 days, which is about, oh, that's too much. Okay, I keep it. Maybe I put it on, let's say 10,000 days, 30 years. And then I have bars. Let me put that I have 400 bars. Then I have reservoir thickness is, let's say 300. Then I have horizontal permeability and vertical permeability at 10 millidarcy. Okay, porosity is 2%, no, 20%, sorry. And total compressibility is normal as it is. Viscosity is 0.8, it's oil. And formation volume factor is 1.2. That is okay. Steffes number is this. If I'm lucky, it will run. If not, then I'm really pissed off. Oh, it's running. That's good. It's quite a big model now. The program is made, the Windows, which is here, is on the Watcom compiler. It's Canadian software. It is using C. A little bit old-fashioned, it can be, but then I have to use another program to redesign it. Watcom compiler C language is calling Fortran. When I press run, then Fortran is running, as it is running still. It's a big model. And then when it is finished, it's 40 seconds, 1 second per fracture profile he needs, you see? So I needed 40 seconds for that. Okay, so let us see if I'm right. If you don't think that I'm cheating you, just a moment. This Hogf is here. My latest file is this one here, you see? It is a very big one. It has 86 and it's done in 42 minutes. So that is done just now. So then I open this file and I want to see these multi-fractures. Look at this. I can see here that this is Hogf model, version 132. Then run is, I'm running from day one. I don't have any oscillation. Here I have some oscillation of the data. Look at this. This is due to Steffes. I do need to tune one number in input data. And I'm getting productivity index of the well. You see? Then I'm getting how many rates? From 1, Q fracture 1, to further. Sorry, okay, let me go to see it. Q1, you just, let us check this number here. Okay, I will do the, oh, you could not see that, my screen, sorry. Can you see it now? Can you see my screen?
Yes, the
Yes.
data.
Sorry, because what I was explaining, I didn't realize that you don't see. I have CS and minuses. That means I have to tune my Steffes algorithm. That means when he was converted to time, he is not able to produce the time without oscillation and noisy data. Okay, now that can be easily tuned, but it is going to be the most important that here, the behaving with time of my rate. You see that it is declining. It is 10/0.5 and it goes to 0.4, and then Q rate is going from 2.4 is going to be bigger and bigger and bigger. He explodes here, but he is consistent. It's 0.8, and productivity index is somehow also okay, I will say. Yes. Okay. Then I look how many individual fracture rates I have. Now I am expecting 40 fracture rates. Look at this. It took him 1 second per each of this rate, but this BS, you remember the BS, the expression for 40 fractures is going to be 10 pages long with Bessel function, and then he has to calculate from this Bessel function this what is coming out of here. So it's amazing work. And here is so this is my individual fracture rates. The most important that this number 40 is the same as the first one. So let us see if it is the same or not. Maybe not. You see. You see that window, I hope? Oh, no. Okay. Then I click here. You see, can you see my snipping tool?
Can you maximize?
I don't know how to, can you see it now, maybe? No, you could not see it. Just sorry. No, okay, just a moment. The results are just the same, you know. So my, I don't know how it is. It is interesting. I'm not able to show you snipping tools because I'm showing you the PDF one. Yes. That's the reason. But what I can do, I can easily do something else. I can easily make in PowerPoint presentation. Yes. On this graph here, I will use this. Let's say, just a moment. I will just I will just copy paste and then give you this, that you see that it is just the same. So I'm going to show you. This is my 40 response. Huh? Why is this? Just a moment. This is my 40 fracture, and then I will just give me a moment, and then I will create the link to the fracture one. So we compare the result that you are sure what I was presenting that it is right. So now, what? Okay. Can you see my screen, please?
Yes.
Okay, so you see, when I enlarge it, you see that the response is equal of the 40 fracture and the first fracture. So when I have here 40 fractures, that means that interference is honored. That means that this one fracture rate is equal to the 40 fracture rate. And that is shown here. This number is equal here, see? This number here is also equal, see? All up to here is equal, you see? So that means that I will have how many curves cumulative? Cumulative, or how many rate curves I will have? Rate versus time, and here's time. I will have here cumulative like this to here to this 20. And I will also have 20 rate responses. This is going to be also 20. See? Why? Because we know that this draining radius is equal to that draining radius, because that is symmetry. Because I'm not including flow in a pipe. I just want to see how I'm extracting from the reservoir to the fracture, because I'm measuring the drainage, you know? And here I'm more squeezed, and here I'm very, very squeezed. So this here is going to be, and this here is going to be for this in the middle two fractures. The last fractures give me the highest one and the highest rate. This is now definitely shown. So that is, it is interesting that this file or my software still work. And yesterday when I was trying to say, should I show you that? Because I thought that was very nice that you see how the simple tool can work. So that is one thing. And then I wanted also one more thing to show you. How much time we have left? Hello?
10 minutes.
10 minutes, okay. Okay, then I will show you only one more thing.
No, sorry. 30 minutes.
Oh, we have 30 minutes. Oh,
Yes.
excellent. Okay, so let us now enjoy another software, very professional one. This one was a software which is more research software, but it is very powerful because even when you have professional software, it can be used to present you to correct the results. I'm going to show you the, oh, maybe I'm wrong here. No, I'm just going to do this. Yes, okay. So I'm going to now, just a moment, connect to existing HLD file, this one here. So as you see here, the software is designed. We yesterday started doing something which was quite interesting. But here, what I'm trying to tell you that here is a GIS system, and this GIS system gives me your coordinates of each well. This well can be vertical, deviated, then it can be fractured well, then it's horizontal fractured, and so on. So this is ideal for as a small database of any operating company, and I'm sure that in Brazil you have a similar thing. You will first be introduced to the GIS system when you have that. Then you can here get the whole area. You can see also here Brazil is here, but I don't have any well from Brazil, but I have surprisingly one well here, which I don't know which one is. It is injection well with a production. I don't know. Okay, let me see what is this. I didn't try it. Huh. Let's see. You see, I have even some data here. Then I can see if I can do any analysis from this data. Let's say if I plot, okay, I have rate versus cumulative. I can maybe make I can have prediction of my rate decline. You see, then I can make prediction of stretch exponential decline. We'll see if I can get it something. No, it is complaining. He needs more data. Or dong decline. Okay, this is, so basically these are the things that, okay, but this was not what I wanted. It was just, I was curious to see if I have any solution from the region you live in, Latin America, of course. So then I wanted to show you, okay, this is one interesting one. This is the gas condensate US case. This is pretty impressive one. Why? Because I have a gas condensate. We know that in gas condensate, when I plot my PVT data, I have first of all to consider the pressure and temperature of the system. This system is amazing. It has 800 bars. It's very tight reservoir. And in metric, I have 160 degrees temperature. I have height of the reservoir, which is small. It's 61 meter. Our radius of the well is about 0.1. Porosity is 7%. Or then as G is big, so I have a gas here. It's a gas solutions. But it is gas condensate. It is rich gas condensate. We can see here. I have here condensate gas ratio in metric. So it is about 2 meter per 1,000 cubic meter. Pressure is bar 170 170 bars, yes. So the rest are really Z factor, how it's calculated, density, and so on. So it is good. Then we have a well bore. You see, I have here the well, which looks like that. You see, it is horizontal well, but it is fractured horizontal well. Look at this. So I have a temperature here. I have the well is deviated. Okay. Then I have well production. You see all the production data are here. And I don't think I have any static pressure. Usually this data are not given so easy. Okay. So now I have to maybe do something more. I can go then to this, okay. And then I'm now in horizontal, but I'm horizontal multi-fractured. And then I want to see the Fetkovich type curve, let's say. See, this is my Fetkovich type curve. So in this Fetkovich type curve, I have a certain decline, which very subjective interpretation. So I don't think the two will have the same person, the same interpretation, but it is always very good to have. Today, this software allowed you that you have another guy looking at your screen, your boss, and you make interpretation, he approve it, and then we go further. So then we can say the history match with skin or no skin. If I put skin, I can see what will happen. Then we have to establish which stem I'm going to use. Let's say that I use the stem of 1, let's say. Then I will make a normalized rate, which is maybe going to be something like that. So see, I'm now getting more probably, or even I can easily move it to 2. Yes. No, not to 2, sorry, then to 0.6. Oh, it's not 0.6. So if I put the stem of 0.8, yes, 0.8 would be quite good one, by the way. You see? So this is going to be my Fetkovich. Okay. Then I want to do the following. I want to use maybe I can also use some other curves as this one. This is the Wattenberger curves. And here I can also make massage of the data by having all this. As you see, there are very many things you can do with this software, but all after all is really what you are after is to get the history match, and then you have to let's say I have here to know that probably I have 20 fracs, accept, and that is going to give you some kind of the describe your system. Now when I'm going to go to use the multi-phase, I will say gas condensate system, multi-phase gas condensate system, then I get something like that. Then I can maybe introduce let's say this data from, but I'm not getting here my X, let's say, yes, you see. So now I'm able to get some kind of the let's say data from any type curve analysis, and then I have here to put my estimate of the size of my reservoir. So now I have a system which is my multi-fractured horizontal well. Here I have to see, I have to know what is my FCD. Let's say that I put that FCD is 20. I don't know if it is going to be right or not. SF is going to be, let's say, FS, where is going to be 2. Okay. So now I have pretty okay, I am pretty, now I want to make the certain prognosis, which will mean that I want to produce it and to see, to make the history match that is going to be happen here. And then I'm going to now make automatic history match. You see the system is now working. You see how the pressure changes here along the fractured well. Look at this. You see? I see that the pressure, which is very high, is going to be yellowish. So it's reducing. So that means I'm producing. Why I'm producing? I'm also in the same time, all the time, trying to change the properties. And once it's finished, I should finally get the best history match, and with this history match I'm going to be sure that I have some kind of estimation of the parameter which I believe they are correct, so that they can be used for further studies. So that is going to be your So that is going to be used in your study. Further, you should go and make a forecast of your study. In this forecast, you should first of all put in the rate Okay, now I fill in everything, but only what I don't have for the forecast in the number of months. So I want to make it for 10 years. And now I'm getting immediately answer. This is my prediction of let's say in this case, calculated gas rate, calculated condensate rate, and calculating water rate. So it is pretty easy tool, and then I can also make more probabilistics. For that, I should include each of parameter to have variation, small value, medium value, maximum value property, minimum, medium, maximum property. And with this, you are able to finalize your project proposal for your manager, and then further it has to go to the management for the approval for whatever decision they want to use. So these are the main things which I think you should know about this. Of course, we have a lot of, I have also one more study, which is refract. That is interesting. Refracturing study. You see? And in this study, I have also maybe to include, let's say that I include Blassingame, you see? You can see here that you have, just a moment that I see how many, I have 15 fracs. Let's say that I want to put 20 fracs. See, he's going to change, I hope so. And then I'm going here to make this change. Half length I will change. I will use only yes. Oh no, I will just then put it on oil. As oil has to be then at least, let's say 70. Saturation of oil I have to change, because he has always to calculate that I'm combining gas and oil. So SO plus SG, SV, because I don't have any water here. So it is equal 1. So it's always 100% is here. And then I can include water. If I include water, I have to put that I have, let's say, 5% water. Okay. So then it is going to say I have 25% gas, 70% oil, and I have 5% oil. And then I have compressibility of fluid. It is okay. So basically, this is then what else I need. Let's right. So this is the one thing, and then also I can go back to the Blassingame. In Blassingame, I can use this, and this. It's not so easy for the first time to understand who is doing what, but you can always start first with the normalized rate, which is probably this one. If you add absorption, geochemical PSS water drive, it will be more complicated, believe me. But this PSS water drive is very important. Why? Because you can see here that what you are doing here, it is initial water in place you can calculate, and what is your aquifer productivity index. These two things are very important for your reservoir, for reservoir simulation. So as you see here, I have a problem with the abandonment pressure. It is not set up. You have also RE over XF, that is the ratio in between, which is not defined. So basically, if you don't have some of the parameters, he will complain and not give you any results. You see, like now. So I will say that with this automatic history matching, at least I'm getting something now. When I now introduce my PSS, you see, with the aquifer water influx, I will move these points. So it is interesting how you are able to define from this simple tool how big is your reservoir. That is what. Why is not that? Hello? Hello?
We are here.
Can you see my screen?
Yeah.
Okay, but I'm not seeing the. Okay, so now, okay, that is why I was in a panic. I thought that I'm disconnected. Sorry for that. Okay, so you see here is the initial water in place. You can calculate what is your initial water in place, what is your productivity index. Why that is important? If this is your reservoir, yes, this is not a PowerPoint presentation, so I'm not able to plot it. At least I don't know how to activate it. But anyhow, what you have, when you have a reservoir with this initial water in place, you will know how much water is coming per certain time unit into your place. And you will know also the aquifer, what is the volume of that, and what is your productivity index, how much water you will bring with the time in the system, in your system, which is oil reservoir. That is how much and fast you will include pressure into your system. So with these two things, you will be able then to make the understanding of the water drive mechanism. With this water drive mechanism, you are going to be able to make the proper knowledge or how to build the reservoir simulation model for the water drive. Without that, you don't know what to do, to be honest. So that is a very, very nice and helpful tool. So this is, and then what I wanted to show you now is that okay, now I'm going to give you a small introduction to fractured reservoir. So naturally fractured reservoir, can you see please my screen? Up to now we talk about, hello?
Hello.
You can see my screen, yes?
Yes, yes.
So up to now we talk about conventional reservoir, but most of the reservoir are tight reservoir, so-called naturally fractured reservoir. So these naturally fractured reservoirs are really what you have here. You have here, this what is here, very dark. This is your matrix. This is your M, and this is your fracture. So the fracture network is very important because why? Once you drill the well here, you have a connection to the fracture network. So these are like multilateral wells because this is big tube. So this tube, which is your vertical well, is now linked to the natural multilateral well, which are fractures, okay? And most of the time you can close. This has to be somehow closed because of the dirty or whatever. So you have to refracture that, okay? So what is now the characteristic? Artificial fracture, we talk about that today, but we model this fracture, artificial fracture. So that we put the horizontal well and then we model it. Up to now, we have something else. We have to make something what is going to be modeled from this multilateral here concept, which is natural multilateral concept. So what is here? So that is the name of the fractured carbonate reservoir characteristic. You have something to do in order to build that system, because this system is characteristical. Why? Because here I am in matrix and here I am in fractured. So that is my fractured system, see? Fracture system. It's like multilateral fracture. Look at this. But it goes everywhere. It doesn't have one point when it starts. So here, so I have network of fracture, of network of multilaterals, you can say. Now I have very interesting thing. Matrix has high porosity and low permeability. This is matrix. This is M. And fracture has opposite high permeability and low porosity. You just imagine. We are talking about corridors. You don't have storage in the corridors because you can put only few guys in the corridors. But you have that usually we run through the corridor and we have a high permeability. We are permeable. Then in a room where we sit, we are not permeable. The permeability is very low, but we have a big storage with it to be 100 people or 50 people. It depends on the conference you have. So that is during the conference, you are in a room which has high porosity or storage, and transmissibility is very low. Opposite, the corridor has high transmissibility, high permeability, and low porosity or low storativity. So this is the dual porosity measure as a measure of complexity of the system. So you have to simplify that somehow. So that was, there were some Russian scientists who came with a model, how they should deal with these unknowns. And they say, okay, we will make the fracture model, which is going to be like this. This is going to be matrix, this is going to be fracture. And then you will go to the reservoir simulator and you will have in the same point of space, one model for fracture and one model for matrix. In addition to that, in order to flow that, we will make a sigma connectivity index. This is otherwise 1 week presentation, but I am just now simplifying it just for you to know. And I want to be very practical because you are very tired today. We have only left 10 minutes, so I want to give you some kind of the end that you enjoy understanding the difference. So here I am. So what is going on here? Usually I can say that this here can be simulated as I have one big layer with a very huge high permeability and another with a very small permeability. And then I plot here rate versus time. So what is going to happen? At the very beginning, this is my initial rate. I will have that these fractures has a lot of oil coming from all these matrices. Matrix has enough time to feed this, and then I will have rate declining, production, and suddenly it is going to stop. It's not going to stop, but it is falling down. The intensity is falling down from this quantity, that is, let's say, 100 to 50. Then, after some times, matrix continue to feed because first matrix fill up all the fracture. This filled up fracture give me the production. Now I need to wait for the time that the fracture feed fractures again, and then it goes like that. So that is typical signature in rate of the naturally fractured reservoir, NFR. Conventional reservoir, opposite, has a very simple answer. Like that. So I am losing this quantity of oil due to the fractured reservoir production compared to the conventional one. Just because of this here, what is, and we don't know what to do with that. We have to model that. In order to model that, I have a whole study which we were developing. We would use so-called image logs, and with the image log, we can analyze the course, and then we count. Let's say one way would be you count how many fracture you have per display, let's say, and then how many fracture you have from that line. See? And then you build yourself your manual model. Once you have that model, you go to the certain book, say the books, and say the book will tell you, okay, give me number of fracture, how big is, what is the shape of the fracture you have? No, number of fracture intensity over layering intensity. And then you can get the shape of the boxes based on these two numbers. And then you build these boxes into your system. That is how you made the system manually. So now I have left only 7 minutes to go through the difference in between conventional and reservoir responses further. This is the first response which you can recognize immediately only from the pattern of rate time if you have a conventional or fractured reservoir. And now we will also look at some other things, and then we will finish. So you see, production characteristic of fractured reservoir. Due to the high transmissibility of the fracture network, pressure drop is very low. You see, around producing well, and pressure gradients do not play a significant role in production. You see, here you have, because why? You need to wait that the matrix is going to feed your system. You see here what is going on. You have a pressure drop is very small, and here you have a huge pressure drop. Look at this. That is the first one. So production is driven instead by complex mechanisms that govern fracture matrix flow communication. So here you have drive mechanism, but you have here that this is hidden by this fracture matrix network, okay? So here is the answer. So the question is now for you, which one is fractured reservoir? Now you answer, fractured reservoir is left, non-fractured reservoir is here, because here I can see drive mechanism. I know that delta P is giving me. You remember that we have productivity index is really delta P here, here delta P. So that is the one thing. Then I have a production characteristic of NFR. It is also another issue in fractured reservoir with some matrix permeability, with some permeability. The pressure decline per barrel of oil produced is low, yes, compared to the conventional reservoir. You see, so you will see that also pressure drop per NME is lower than in conventional reservoir. See, that is also fractured, non-fractured reservoir. This is more to the so-called fluid expansion, gravity drainage inhibition, provide a continuous supply of oil from matrix block into the fracture during production. So this is a bit to go into the reservoir engineering, which is very important discipline. In order for you to be an expert in reservoir engineering, you need several courses. Among them is this one, reservoir engineering. Then the GOR, fractured reservoir normally remains lower, the GOR, through production, throughout. See, the liberated gas flow preferably upward through fractures. That is. So the GOR is lower. So that means you will get a huge production of gas in the well, but in the system, looking the whole system, GOR will be lower. But at the well, system will be producing a lot of gas because network is multilateral well, which is now producing to the producing well gas, and then gas oil ratio is lower than should be normal. Okay. And then gas cap, you have to see also the gas cap. That is what I was using. That all gas is going to go to the gas cap, so the rest is going to be GOR, which is going to left over in the reservoir, will be lower than when I have a conventional reservoir. Then what is very important, that transition zone in between certain fluids, that means in between water and oil, which is usually somehow defined by the water oil contact or gas oil contact, is not going to have any transition zone. There is no capillary pressure. That means that that zone is flat. So that is also important. And then production characteristic of NFR is also water cut in NFR is function of production rate. That is important. And we don't have any effect to water production of petrophysical characteristic of the system or PVT properties of the fluid. So there is no so the only what is dominant is production rate. And then also production characteristic of NFR. When we talk about PVT, NFR PVT properties are constant. So this is fractured reservoir. They do not vary with the depth, as in norm and is in non-fractured reservoir. So you see here, here I'm constant and I'm in fractured reservoir. But this here is, as you see, non-fractured reservoir, the other two. So with this, And then further, the last thing is to talk. I was also very fortunate in my career. I was running 2 workshops. Usually this workshop, a 5-day workshop. So I will be willing to have a whole workshop with you guys on fractured reservoir only, because fractured reservoirs is also your future, particularly due to the non-conventional reservoir. So fractured reservoir, and one was the workshop in Dubai, and another one was workshop in Istanbul. Otherwise, I was lecturing naturally fractured reservoir at University of Lorraine, because you see that you can find me on the LinkedIn as Branimir Cvetković Brel, because my mother family is French. So that is, I was very fortunate to be lecturing at the university for 7 years in France. You have such a course lectured by the guy who is one of the best experts in geology. They speak up with the expert in a certain region. Then another in flow simulation. My duty was to talk about what I was talking today, how we couple wells to the reservoir, particularly naturally fractured reservoir, in order to characterize such reservoir and to increase production. So that was my role. Here, the last is what I want to say. When I have, we have to characterize fractured reservoir. We can say fractured reservoir is all matrix. Then I have fractured reservoir number 2, which is partly matrix, partly fractured. Then it is more fractured, less matrix, and finally all fractures. All is fracture network, like multilateral well. So here I'm decreasing matrix, and here I'm increasing matrix towards here. So here I have, on this I have that I'm 100% fracture, and here my porosity is 100% fracture. You see, that is how they made, Nelson did this classification. So this is my total porosity and total permeability in addition to that. So that was all what I wanted to present today. Here is, of course, more about how you create fractures. Today we spend a lot of time discussing about omega, about this height, about the half length. We talk about here about this special conductivity, dimensionless number. We know now that this is a link in between fracture permeability and width, and system or matrix system permeability and half length. And then to make the proper, when we are fracturing, we have to have this knowledge of this coefficient, because here with a certain knowledge about also the structure, how this fracture 2xf is related to the size of the reservoir, I can then create the fracturing model. And this is the whole scenario, how you create the fracturing of the model, see, with this formula. It is really this number multiplied by the T that is going to give you how much propan you are going to inject in order to get some effect. And here also, if you go more, then here we went through the system, how we are saturating. And this is, I would like to thank you for your attention. I'm somewhere here at the top of this is in Stavanger, that is close to, on the sea. It is a beautiful city. It is like probably Vitoria, the center of exploration. I hope you will be soon also the center of exploration of oil and gas, because you are living close to the very many assets. And it is nice, whoever come, we can once go and climb, and you can sit here. So this is a pulpit rock, Preikastollen, above Lyse Fjord. That is one of the fjords nearby Stavanger, which is a beautiful place. All is made in wood. Otherwise, regarding the literature, I am willing to share with you something, and then I finish. Just a moment, because I promised you last time. Usually I like to keep my promises. So let's say. So here is, hello?
Hello.
Oh yes, okay, you are still with me, okay. So I just wanted to give you also a few things which I wanted to give you as exercise, home exercise to read it. So,
Professor
just a moment.
Branimir,
Yes.
I'm sorry, I'm some late because we are having a microphone here.
Okay.
But I think it's solved now.
Okay.
I have to disagree with you. I'm so sorry. But Victoria, it's much more beautiful.
I see. There is no doubt. There is no doubt, you know. I must say, when I see this, you know, crude, the small bar when you can have fish, and you early morning go along the beaches, and then no, there is no comparison. You know,
Okay.
I have a daughter, and she loves Brazil, and she's is it samba you are dancing, or what is Brazil? Samba? I never know. Yes.
Yeah.
No, so she's a teacher, even you know, you should invite her. She's excellent, by the way.
You are expecting to have you here again. It's a pleasure to hear an expert in so interesting subject. Congratulations for your course.
But thank you very much, because I appreciate it. As I said, I was there thanks to Marcio sometimes ago, and then this time I was also invited, and I am very, very happy that I managed to contribute, you guys. Some of the guys from that course get job in Petrobras. Particularly, I remember one who was very good in mathematics, by the way, and I was very glad to hear that he is in Petrobras. It doesn't mean, but anyhow, I wish you, look, guys, with your mechanical background, you have open door to petroleum industry, particularly when it comes to the pipeline, to very many things, not only pipeline. Production engineering is your subject, by the way, in petroleum engineering. You just have to learn few courses, not more than 5 courses, you are an expert. You have to dig more in PVT, you have to dig more in geology, geophysics, reservoir engineering, production engineering, petrophysics. That is all. I don't think that I forgot anything else. Yes.
Okay. Professor Márcio Martins is among us now. And
okay.
he will...
Thank you, Branimir. Thank you.
So
Thank you so much.
But Marcio, I promise, and I will send you, I would like that you distribute what I promised.
Okay. You can send me, I distribute after.
So this is a nice, let's say, backup for them. And also, I only need to find one more booklet, which is going to give a good introduction. They can read with the if they follow the course, they will understand it fully. You know.
Perfect. Yes.
So this is from me, and wish you all the best for your continuity and for your
Thank you,
efforts. It is appreciated, and I am very honored to be part of this conference. And thank you.
The honor is our honor to be you here. Thank you. Thank you.
Thank you, and all the best, guys, and particularly to the ladies. Next time you send me the picture of all participants, please. And names.
Okay.
Yes. Okay. But all the best, Marcio, and thank you all the best.
All the best, Branimir.
And
I'll call you the weekend too.
Yes. The same.
Okay. Thank you.
Okay, bye. Cheers. Bye.
Bye. Thank you.
Thank you, Mr. Brown. I learned
No.
so much. Thank you.
Thank you. It's my pleasure to be with you. Bye bye. Bye.
And let's remember to the rest of attendants that the Congress continue, okay?
Yes. Okay.
For more 2 days here in Brazil.
Okay.
Unfortunately, Professor Branimir stopped now.
Okay. Okay. But thank you and all the best.
All the best and health.
Just a moment.